All right, let's chat. How's it going with the homework?
Good, good. It's very interesting. SDPs are a little tricky sometimes to get right, I think.
Yeah, that's true.
Yeah. Can we go through maybe problem 9.2?
It's what, 9.2?
Yeah. So actually before 9.2, because 9.2 is like probably harder. In 9.1, can you, I mean, maybe I'm missing something here, but like to me, isn't this just a Chebyshev center kind of problem? Or is there something, is that like not the right intuition? Because I mean,
I don't know what Chebyshev center means, so maybe it is.
oh, sorry, yeah, it's like the convex optimization thing where it's like the, like, I mean, I just like copied it from like Boyd and Vandenberg. It's the, what is it? It's like the maximum inscribed. It's the distance to the closest point in the exterior of C. Yeah, I'm not sure. Yeah, so basically my intuition there was just like um you just have to formulate LP, where the
Yeah.
LP is based on the how far away from the constraints you are at any given phase. And then
Yep.
yeah. So I guess that one's okay. Maybe we can just do 9.2 then.
Okay.
So I think I got like A and B were relatively simple, but then in C, finding the SDP relaxation, I was kind of struggling to show how the part B like ended up giving being equivalent to like an SDP constraint, like a matrix SDP constraint.
Okay. Let me
Yeah,
reread it because I haven't looked at it since I wrote
yeah,
it.
no worries.
Yeah. Okay, we got the jobs, we got the constraints. These are like the betweenness constraints. All right. Suppose that we are given a perfectly satisfiable instance. Prove that the following quadratic program has a feasible solution. Okay, did that work out for you?
The
Part B?
part B.
Yeah.
So that from what I understood, that was just like arithmetizing this kind of problem in some sense. Like it
Yeah,
was just like converting like
basically.
x just becomes a vector where the vectors hold the j1 through jn, and then like just the constraints, like if you just like write out the constraints, then this just becomes arithmetization of the problem pretty much.
I see. So like what is xi supposed to kind of stand for?
Ji and xj is jj, maybe. At least like that kind of, because it's like xi minus xj then have to be at least an integral distance apart. So the square must be at least greater than equal to 1. So that one was just satisfied by time slots being integral. And in the second one, either either one of this is negative. Sorry, either xr minus xs is negative or xt minus xs is negative, and the other one's positive when the constraint is satisfied.
Okay, so well, let's just make sure we're on the same page here.
Yeah.
So like right. So what a when you have a perfectly satisfiable instance, like how will you assign the xi's to get a feasible solution?
So the xi's would be one where the so xi would be ji, right? Like that's how I was thinking about it. Where ji is the like the
Yeah, it's
schedule
just
or
like
like
the
the time
name of a
slot.
job, though.
Oh, I
It's not a
mean,
number.
wait, but then like isn't the constraints of the form jr minus less than equal to js? So how can you have that for just the name?
I see. Well, I guess you're saying that you're like you're supposed to, I guess, I guess you can say you're supposed
Yeah,
to assign numbers to the j's.
yeah. I mean, I'm not sure because like the question itself says if you have the constraint of the form jr less than js, this is my assumption was that it's like the number assigned to J
Okay.
after n. So I was just like maybe abusive notation.
Okay, I
was
got you.
thinking
Yeah.
of. Yeah.
Okay. All right.
So yeah, maybe I was just thinking xi would be the time slot assigned
Right.
or the schedule assigned to job J.
Okay.
Job I, sorry. Yeah.
Okay, good.
Yeah. So yeah, I mean, I think if you do that, then the first constraint is just satisfied by the fact that like the time slots are integral distance apart, pretty much.
Yeah.
And the second constraint is satisfied because
Well,
like
the sign
either
business works out. Or
yeah. The sign will like work out because either one will be negative and the other will be positive.
right. Okay.
Cool. Yeah. So that was that one. But then for like formulating the SDP, we were thinking about how to like come up with a matrix that represented this, and it was slightly because you can't necessarily use the same like x vector shown in part B because that's one vector for the entire schedule versus like in part C you want like one vector for each job. So we were thinking of using like one hot vectors for the jobs where the where like job I gets a vector where it's one a vector in n of n dimensions where it's one for the position it's scheduled in some sense. Does that make sense?
Okay, so you're formulating like you have the idea that you want to set it up so that maybe you have some vector j vector I, which looks like
yes, exactly
1 0
1. Yeah.
Okay, so this is your idea to have this as a feasible solution.
Yeah. Like have this like have the vector assignments end up being some feasible solution. So like yeah.
Okay.
And then like the idea was if you stacked all of the j vectors together and then did like some j transpose j or something like the matrix of the j vectors transposed with its and multiplied by itself, then potentially you'd get like something that satisfies this, except like it's hard to do ordering on ordinals. It's hard to do ordering on one hot vectors.
Like this?
Yeah, exactly. So it's like we call this maybe like script J or something.
And
then
J transpose J.
Yeah.
Okay.
Yeah. So it's either that or like exactly. That was like the idea. And then kind of we weren't that's kind of like I think what we had and then kind of so this would kind of give us the first constraint would then be this is equal to the first constraint was something like script J transpose script J minus I is positive semi-definite, I think.
Okay. So is your idea here that like you want to find some positive semi-definite constraints that will be satisfied by this proposed solution?
Yeah, like basically the idea would be if you are able to reformulate part B's like objectives in terms of some positive semi-definite kind of matrix constraint, then it could just be like written as an SDP in that form.
Yeah. Well, I mean, one thing, this could be good, although it might not be answering the question directly as asked, which is to like formulate an SDP relaxation of like this quadratic program, meaning like this one. So it's probably, it could be fine. You're formulating a semi-definite programming relaxation. It's kind of asking you to formulate a particular one, but I don't have to be picky about it. But it is true that like I guess the intent was that you'd be like motivated by part B.
Right. I see. So would this be like, so the SDP relaxation of this the part B semi-definite, the part B quadratic program, would that be like based around the idea like, so when we're formulating the SDP relaxation, that's usually like assuming that the xi's, which are real numbers, are vectors instead of that's usually that's like how Max Cut did it in some sense. So is that like,
sorry, yeah, kind of, although if you remember how we came to the semi-definite program from Max Cut originally, we kind of thought it was like a quadratic program where we're trying to maximize like this expression, sum over edges,
right,
UV, some quadratic expression like XU, XV.
Right.
We had like XU squared is 1 for all U. Excuse me. And the idea there was we wanted to like, since this is quadratic, it's not linear, it was a problem. So we wanted to introduce some variables like Y, UV, that were supposed to stand for XU times XV.
Right.
And then this business became equivalent to like maximum sum over UV and edge of this, which looks linear.
Yeah, that's right.
And we have this linear constraint as well, YUU equals 1. But then we try to enforce this other like last constraint, which is like, sort of there exists, reals XU, 1 for each vertex, such that Y VU, UV equals XU XV.
Right. That makes sense.
And
yeah,
this was not a condition, but we relaxed this to this semi-definite programming condition, or this PSD condition, that like the matrix Y formed by the YUVs is PSD. And I guess we argued that like, okay, if you have this property dagger that the Y's, the YUV, equals XU, XV for some real values X, then this matrix is positive semi-definite. Not necessarily the reverse, but like that's why it's relaxation.
I see.
And the thing is, like, once if you do this relaxation, then you see one thing you could see is that if you're gonna like just accept the fact that all right, we're gonna take this as a relaxation, then in your original program, like you can have the expression like XU dot XV appearing anywhere. Like if it's gonna be replaced by YUV, then as long as it's like, I shouldn't say anywhere, but like as long as like these expressions are appearing linearly, then you could have lots of constraints involving them. You can have the objective function involving them. So this is kind of like the generic way to relax a quadratic program to a semi-definite program.
Right, that makes sense. Maybe I'm like a little confused about the relaxation from Dagger. Why again does the relaxation like work? Like why do you have like, if there exists XUV, if you have like Y uv is equal to xu xv, then y is positive. Like why does it necessarily have to be positive semi-definite? It's only if we're assuming xu and xv are integral, right?
No, not necessarily. So let's do one direction. So if like the y UVs are such that there exists x u's with y uv equals xu xv, then this y matrix is positive semi-definite. I suppose the easiest way to see this, or like a linear algebra way to see this, is if you write the x vector here.
Oh, I see.
And then write like this, x1 xn.
This is the Cholesky decomposition thing.
Yeah, you'll have this. I mean, this will equal y.
Okay, that makes sense.
Because like the yuv entry here is like xu times xv.
Right.
And so this gives a way of writing y as like a matrix times its transpose. And that's one condition for being positive semi-definite.
Right. That makes sense. Okay.
Maybe the most standard of all condition way to phrase it is, y is PSD if and only if, well, I guess the most usual definition is like for all vectors z transpose y, z is greater than or equal to 0.
Right.
But if we have this equation, then we could say, well, for this particular y, z transpose yz equals z transpose x times x times z. So maybe I'll draw it like z as a column vector. That would be like z, and then this would be like z transpose like this. And then this is indeed like greater than or equal to 0 as like a number, because it's like well, it's the inner product between z and x squared. Is the simplest way to see it.
Yeah, that makes sense.
So that's one direction.
But that's the only one that we really need, right? Because that's the relaxation.
That's a relaxation. Yeah. But then to connect it up to like vectors, one thing I might do is, okay, let me go back to this true fact that I just put a check mark by. We just draw a little dot there that stands for a multiplication of two numbers.
Right.
This is true. So now the converse is not necessarily true, that if you have some real numbers such that, if y is PSD, then there have to exist real numbers that make this true.
Okay.
But what is true is that if y is PSD, then there have to be some vectors in N such that this is true, where now this dot means dot product.
That makes sense. Yeah. Okay, that makes a lot of sense. Cool. Yeah. So then like going back to the 9.2.
Yeah.
That like kind of inspires me to think of the xi minus xj as potentially being some like vector, because then technically we're talking about the like it seems like there's a dot product between vectors being less than 0, and then there's like a vector squared, which would be like the relaxation would be it's like it seems like it could be xi minus xj becomes some vector indexed by I and j. Does that seem like, because then it seems like it's like somewhat similar to the max cut kind of SDP formulation.
Yeah, well, the most mechanical way to do it, if you have like any quadratic program. Well, first, like, maybe I didn't make things very clear. First of all, I guess I would say like, did I define what really is a quadratic program? Or if so, do you have in your head like a good definition of what a quadratic program is?
Yeah, it's like the minimization over some quadratic, like some quadratic program, which is like I mean, I'm thinking Hessians and ellipsoids in general, and like minimization over that.
Well, those are more like algorithms. Actually, so maybe, okay, maybe I didn't even explicitly say this in class, so it's maybe good to say it. I mean, for me, like quadratic program is like, basically same as a linear program, except the constraints, that's not good spelling, constraints and objective can be of degree 2.
I see, that makes sense.
So a linear program, they're supposed to be of degree 1. So like, you have constraints that look like, 7x1 plus 3x2 minus 5x3 is less than or equal to 9. And then some other constraint like 2x1 plus x2 minus 8x3 less than or equal to minus 4. And then maybe you have some objective that's like, maximize or minimize. I don't know, x1 plus x2 minus x3.
Yeah.
So these are all like linear expressions in the x's. In a quadratic program, they're just allowed to be quadratic. So you can have, degree 2. So you can have
some squared or something.
Yeah, you can have like x1 squared, and you can have like, x1 times x2, and you can have like x1 times x3, and then like in the objective function, you can have like x2, x3 plus 5x1, x2 minus x, that's not an x, x2 squared or something like this.
I see.
So that's a quadratic program.
That makes sense.
So I guess the relevant thing here is you can think of like a quadratic program. It's like, you can also say it's like a linear program. Okay, maybe I'll be a little informal here, but it's like a linear program, but where the variables can be like products of 2 variables. That doesn't quite make sense, but maybe I guess you know what I mean.
Yeah.
So, and this is a situation where like, so max cut is like an example. Here was our quadratic program. Because it looks like a linear program, except that like, where you would expect to have like 1 variable, you have like the product of 2 variables.
Right, that makes sense. Yeah.
But whenever you have such a quadratic program, like you can try this idea.
Oh, okay. So like you can write it in terms of some okay, that makes sense. Yeah, that follows like with what I was like thinking. I think my intuition was, because now it seems like the quadratic like part, I guess you could expand this in terms of and the xi minus xj, the whole squared, gives you some quadratic thing, and the xr minus xs times xt minus xs will also give you some like quadratic constraint, and then each of the terms there give us like some like quadratic constraint, and that sorry, they're at least they're of or degree 2. It gives you 2 degree 2 kind of polynomials, and that we can probably exploit using this trick.
That's exactly right. Yeah, that's what I was, sorry, go ahead.
Sorry, yeah, I was just asking if that sounded like correct.
Yeah, that was in fact exactly what I was going to ask you. I think you answered it without me even asking it, which is, so it's actually not like extremely plain on the face of it that this is a quadratic program. Like, okay, I say in the thing that it's a quadratic program, but it doesn't look exactly like this thing I just said here. There's the definition of a quadratic program. But as you said, yeah, you can just, if you expand this out, like, xi minus xj squared greater than or equal to 1, this is the same as xi squared minus 2xi xj plus xj squared is greater than or equal to 1. And this does look like, the kind of thing that I said you're allowed to say.
Yeah, okay, that makes a lot of sense. Cool. Yeah, that makes sense. Interesting. I was thinking about this in a very like different way. I was trying to create like a matrix that would like constrain this, but this seems like a much more straightforward approach. Thanks.
Yeah, sure.
Yeah.
So yeah, I guess you'll find that like if you take this idea ahead, then like generally you can think of like a semi-definite program as like a linear program, but where the variables can be, well, maybe this is combining several steps, but like where the variables will be like dot products of mystery vectors.
Right.
Because if you
So
sort of
we're
like
doing
replace
the
like,
relaxation. Yeah, sorry,
this
go
with,
on.
I was just gonna say, if you replace this with yij and this with yjj and this with yii, and then you do this relaxation, then a solution y will be PSD, and that means you won't necessarily have like real numbers x's such that, you know, y uv is xu times xv, but you'll get vectors such that yuv is xu like dot product xv.
Cool.
Yeah.
That makes sense. Thanks.
Sure.
That's really useful.
Okay, cool. All right. Let's pause there. We can come back to it if we like. Is there another question somebody would like to ask about?
I was stuck on 9.2D.
Part D, I see. Okay. This one here?
Yeah.
Okay, let's see. What does it say? Assume that you can use the ellipsoid to find a feasible vector solution given a perfectly satisfiable instance. Show how to get this approximation algorithm. Okay, so it's some kind of like rounding question. So maybe you can tell me like, at least according to how you did it, like what is like the meaning of like a perfectly satisfying vector solution, like maybe geometrically or in any way. Like, what did that mean? Or you didn't get to that part yet?
Wait, I was just thinking that, oh, like, I wasn't really thinking about it in terms of a vector solution, but more so like there is you can schedule the jobs in such a way that you satisfy all the constraints. But I didn't really extrapolate that to like the vector solution.
I see. Maybe we should go back to C then. I mean, did you solve C?
Yes.
Okay. So it gives you some kind of vectors, right?
Right. Well, my thought was in part B, I kind of took the variables to mean like the time in which the job should be scheduled. Right. So I wanted the vectors I was hoping that the vectors would represent that as well.
Perhaps, yeah. Well, in some way. But maybe we should talk about, I mean, what was your formulation?
Oh, so I mean, for part C, all I did was just like take like all the variables, and so any like xi times xi would replace by y I in a matrix y, and then xi times xj would just be replaced by yij. And then I had the constraint that y had to be positive semi-definite. And then the vectors would just be, since every position in the matrix is the dot product of the two vectors, each job is just one of those vectors.
Okay, yeah. Okay, so but I guess what I'm saying is maybe it's, what properties do these vectors, what properties do you know they satisfy?
I know they satisfy that. Well, just sorry. I think I only that like every like basically what I said before, that every position in this positive semi-definite matrix was the dot product of two vectors, and that's about it.
Yeah. Okay. So all right. Let's write down the SDP you have in mind. So maybe you tell me what to write, and I'll write it.
Okay. So I basically have the expansion of. Okay. So let me just say. So I have YII plus YJJ minus 2 YIJ. And greater than equal to 1. And then YRT minus YST minus YRS plus YSS less than or equal to 0. And then Y is symmetric and positive semi-definite.
Okay. Okay. Cool. Great. Yeah. Okay. So now, yeah, the next question is, what does this have to do with vectors?
So every position Yij is equal to like vectors, I guess, xi dot product xj.
Okay, good. So yeah, this is equivalent to, the existence of some vectors x1 through xn such that this holds. So in particular, for example, that means that if you solve this and you get a solution, you get some vectors, then, for example, we know that xi vector dot xi vector plus xj vector dot xj vector minus 2x vector I dot x vector j greater than or equal to 1.
Right.
So, okay, we might ask ourselves, like maybe more intuitively, what does this mean about these two vectors?
Sorry, is there supposed to be like some property about vectors I should know?
Well, there may be some simpler way to think about this. Oh, we can do an example though, like here's R2. Let's say, I don't know, this is xi, and I don't know, this has length 2. I'm just making this up, and I don't know, this is xj, has length 1. I don't know. So do these two vectors satisfy this?
No.
Okay, why not?
Okay, so the dot product represents the magnitude, right? So, I mean, if you take the dot product of itself.
It's a squared magnitude, yeah.
Oh. Wait, sorry. Okay. My linear algebra is kind of shaky.
That's all right. So, all right. Well, how much is this?
This 4.
Yes. How much is this?
1.
And well, I didn't exactly say like what are the angles here, but let me start with this. Is this positive or negative?
This is negative.
Yes. So then this is
Okay, so it's
positive. So this is like 5 plus a positive thing. So that's bigger than 1.
Right.
That's good. What if xj were like, what if this was also xj? What if they were both this vector? Then what?
This would also satisfy. Oh, sorry, it wouldn't satisfy since it would. Wait, sorry, the angle. Oh, sorry, yeah. This wouldn't satisfy since xi dot xj would just be equivalent to xi dot xi or xj dot xj. Right, so this would just equal 0.
Yeah, this is before, this would be 4, this would be 4. So you get like 4 plus 4 minus 8, which is 0. So actually it wouldn't satisfy because 0 is not bigger than 1. There's not at least 1. Does that make sense?
Yes.
Okay. Yeah, okay. So, what can we, I mean, still is a little bit mysterious, I guess. I mean, if I said like, what about this one? If this was like xj, would it satisfy? That's a little hard to say. Actually, yeah, so what is the, I mean, what can we make of this left-hand side?
So it's kind of like the sum of their squared magnitudes minus 2 times their angle between them ish.
Yeah, that's true. Actually, how do we come to get this expression in our hands anyway? Where did it come from?
Just from the original constraints in part B.
Which was what?
Which basically said that they had to be at least a distance of 1 from each other.
True. That's true. The original constraint did say that like as real numbers, like the distance of xi from xj had to be at least 1. Well, did it say that actually? Yeah, I guess it did. What's the distance between xi vector and xj vector?
I think it's the dot product of 2 vectors. Sorry, me.
Yeah, so we have xi, like xj, We want to know the distance between them. It's like the length of this yellow dashed thing. Yeah, it's the length of a certain vector. Which vector?
The yellow vector.
Yeah. How do I express it in terms of xi and xj?
Oh, xi minus xj, the dot product of xi minus xj times, or xi minus xj and then dot product by xi minus xj.
Yeah, that's the distance squared. This is like the length of a vector of v squared is like the dot product of v with itself. This vector here, if we like orient it like this is xi minus xj, or maybe it's the other way around. I think it's xi minus xj. Yeah, so the distance, I guess, squared between these two things is this expression. How does that relate to this expression?
It's the same thing.
Yeah, it's the same thing. So this thing here is this thing that we're kind of getting. Also the same as like the distance between xi vector, its tip, and xj vector squared. It's greater than or equal to 1. So that's a little bit more enjoyable. I guess if we looked at these like pictures, we're doing some examples here. I guess we first looked at like this case. This was 1 and this was xj. And yeah, it seems pretty clear their distance is bigger than, from here to here is bigger than 1. And then we looked at this other case where like these were both xi and xj. And I guess the distance from like here to itself is 0, so that's not bigger than 1. Okay, so that's nice. What about this one? What's going on with this one?
I mean, if we did something similar to what we did with the first constraint, it just translated back to like xr minus xs dot product with xt minus xs.
Yeah, xt minus xs. That's right, it's less than or equal to 0. And I guess like, let me just so we have it, in our minds, this could also be written xi minus xj dot with itself. Sorry, this is getting messy. Xi minus xj is greater than or equal to 1. So yeah, it's kind of like, if we have a solution to this semi-definite program, which is like this matrix of y, then it's equivalent to like having some vectors that satisfy, I need like a nice color here. Like this, whenever RSTR is a constraint, and also this. So actually you see it like depends a lot on like these differences. So like, let's say like, say we just have 3 variables or 3 jobs and like, I don't know, 1 constraint. It's like R is supposed to be less than S, supposed to be less than T. And okay, so then maybe we solve this semi-definite program and like get some vectors X. Let me just call them, I don't know, okay, 1, okay, R. Let's say there's only 3 of them. So R vector, and X, S vector, and I don't know, XT vector. So yeah, how can we, I mean, Okay, so so apparently they satisfy these properties in pink boxes, but maybe we should just think a little bit about what that sort of means. So let's start with this like pink box. I guess it said the distance is squared or at least 1. So I guess in this picture it means that like apparently like this distance is like at least 1. Like this distance is at least 1. And I guess this distance, this diagram's getting messy, at least 1. And what about this one? What is this one kind of saying? Let's rewrite it over here. It's like xr minus xs dot x. What was it?
T minus xs.
Okay, minus xs less than or equal to 0?
Yes.
Okay, let me erase the screen stuff. Okay, so what's xr minus xs here? I guess it's a little hard for you to say because like you can't look at the picture, but it's some vector here.
Okay.
Which one?
Like the vector between like where the arrowhead of xs and xr are.
Yeah, so it goes like from here to here. And what about this one?
Between like the vector between going from xs to xt.
Perhaps the other way around.
Or
maybe it is the way you just said.
oh,
I should get this right. From xs to xt. Yeah, no, I think you're right. That's right. Okay. Okay, so that's this vector. What's this vector? What does it mean like their dot product is not negative? Does this have like some kind of meaning?
that their angle is at least 90 degrees.
Yeah, that's right. And they make like an oblique angle, as they say. So actually, like almost everything that we know only depends on these difference vectors. I guess it's almost nicer to think of these vectors, these yellow vectors, to just identify them with their like endpoints, their tips or whatever. So like, I don't know if this is the origin. Maybe that doesn't matter. Like this xs vector is maybe more like this point. Oops, I was going to draw it in yellow. And this xr vector is more like this point. And this xt vector is more like this point. And the things we knew, that like xs minus xr dot xs minus xr is at least 1, kind of said that like this distance is bigger than 1, like this distance is bigger than 1, this distance is bigger than 1. And then this constraint kind of told us that like this vector, this green thing, and like this green thing make an oblique angle. Actually, they don't make an oblique angle in this picture. Looks like they make an angle slightly less than 90 degrees. So I guess it means like this actually wouldn't be like a solution that the semi-definite program that was feasible for the semi-definite program. I guess to like draw a solution that's like feasible for the semi-definite program, you'd need like I guess you need like a triangle, like 3 points that like made a triangle, and like there should be like an oblique angle at xs. And I guess the side lengths of the triangle should be at least 1. And I guess you'll have some kind of like oblique angle constraint for all the like constraint strains that you had in your original problem.
Mm-hmm.
It even kind of makes sense with like the original version where like we were plotting all these J's positions like on a line. Oops, I don't know what I'm saying here. J5, maybe this was like J4, and like J6 was here. you know, if we had the constraint that like J3 is supposed to be between J5 and J4, which we got right, it is sort of like, actually, I mean, if you look at it, the, you know, the angle between like this vector and like this vector is oblique. Well, it's not just oblique, it's like 180 degrees, but that's in particular oblique. And the side lengths are all at least 1. This is like 1, and this is 1, and this is 2. Although actually, you know, like this constraint were about J6, then, you know, this, well, these side length would still be at least 1. And this would be longer. So like the, I guess like, you know, a feasible quote unquote vector solution is like similar, except that like these vectors don't have to all be in like the line. They can be like sticking around in space, but somehow the condition is about, I guess, these triangle side lengths being bigger than 1 and like having this oblique angle constraint whenever you have one of these betweenness constraints.
That makes sense.
Okay, yeah. So okay, this doesn't really solve anything, but like, I mean, it gets to, I guess, you know, this is like the key step, well, a key step is to just, I guess, sort of like figure out what it, whoa, sorry. Figure out, you know, this feasible SDP vector solution, like what it really means, or like, you know, how to think about it. So in some sense, there's still the remainder of the problem. Like, okay, so like, it's kind of like, okay, if you had, you know, it's like the SDP solver proudly comes back and gives you these vectors or these points in space. Where are they? I can't find them anymore. Oh, here they are. Well, no. Okay, I can't find it. Oh, there we go. Yeah, it's like the SDP solver may like come back and like proudly give you all these points in space and say, look, I did such a great job. Like all these points, maybe they're a distance at least 1, and like whenever you wanted me to have, you know, J6 between I don't know, J3 and J10, I managed to find like, or I managed to set it up so that like the angle between these two lines is greater than 90 degrees. You know, you might say, thanks very much, SDP solver, that's great, but like I really wanted to have actual schedule, you know, I really want to picture more like, you know, this, where like they were all on like a line. So now you need a bit of creativity. Like if you have all these points in space, how can you actually kind of get a real solution where they're actually a schedule for these J's at these various times that ideally like satisfies all the original betweenness constraints. Now, you know, if you look at the problem, you're actually not, it doesn't insist that you find a perfectly valid solution. You only have to find like a pretty good solution where like at least half the constraints are satisfied. And you know, this could remind you maybe a little bit of the Gomans, Williamson, Max Gut thing, where I gave you some vector solution. You're like, well, this is great, but I really want like an actual integer solution or like an actual partition of the graph into 2 parts. You have to like figure out some method of like taking these high dimensional solution and converting it into a regular solution that's maybe in some sense not that much worse.
Yeah, okay, I think that makes sense. Yeah, this is very helpful.
Okay, great. Yeah, so some creativity is still, you know, required, but yeah, hopefully you'll have some maybe somewhat geometric ideas maybe that could help.
Okay, thank you.
Sure. Do you want to ask about any other question?
No, that was the only question I had.
Okay. Well, I guess we can call it a day then. Thanks for coming by, and I'll see you tomorrow.